Okay, I'm re-recording this from my office. There was some technical issues today in class, so I'm just going to record a quick review of today's lecture. Just to remind everybody, so homework 4.1 is due today. 4.2 is due on Wednesday. We are not going to have class on Friday because of the fall break. Next week, we're going to finish out our topic on Monday, and then we have exam review Wednesday and the exam on Friday. The assignment next week, 4.3, won't be due until Wednesday, so you'll have a little time between when we come back from break until that assignment is submitted. So today, we're going to go back to rigid body equilibrium. We're going to continue the example that we left off with last time, which, as you may recall, is this example. So just to recap, everybody, so we have a fixed crane here that has a mass of 1,000 kilograms and it's used to lift a 24 kilogram box. So right off the bat, we are converting the kilograms to a weight by using mass times gravity. And so remember, gravity is 9.81 meters per second squared. We have a pin at A and then a roller at B. And so what I've done is I've drawn this as a free body diagram that you can see here. I haven't drawn in the actual members of the crane, like as you can see these sort of members right here. It doesn't really matter as long as you have the load at the location of the center of gravity that's indicated in the problem. And speaking of this term center of gravity, we are going to define this more rigorously a little bit later when we look at centroids. Okay. So we're just going to jump right into this problem, and we're going to jump into it by going ahead and solving out the reactions. Now, I mentioned this in class last time, but I've drawn the three reactions. I drew this vertical reaction going upwards, and these two horizontal reactions, I have them both going to the right. And I'll go ahead and tell you that one of these is, in fact, wrong in terms of the assumed direction for these one of these reactions. And we're going to see this probably pretty soon. So let's go ahead and jump right into it. And so what I'm going to do is I'm going to write the equations of equilibrium, and I'm going to write them in the sort of standard order. So we'll start out with the sum of the forces in the x direction equals 0. And we'll assume forces to the right are positive. And if we look at the problem, I only have two forces acting to the right, and that's AX and BX. So AX plus BX has to equal 0. And I'm doing that because they're both acting to the right, so they're both positive, and so the sum of them must be 0. So I'm going to call this equation 1. And right off the bat, that should tell you that there's something amiss here, because if I have two quantities, like x plus y, and the sum of those has to be 0, well, one of those has to be negative. And the fact that I've got them both as positive means that one of them is my incorrect assumption, as I mentioned earlier. All right, so summing forces in the y direction, let me do that in black. So if I sum forces in the y direction, and we'll assume forces acting upward are positive, I'm going to have AY going upward. I'm going to have 9.81 kilonewtons going downwards, and I've got 23.544 kilonewtons also going downward, and that has to equal 0. I don't have to consider the horizontal forces because this is a sum of forces in the y direction. So add both of these terms over to the other side, and I get AY is positive, and if I add these up, I get 33.35 kilonewtons. That's just adding up these two terms over on the other side. And so that is our next equation. We'll call this equation 2. Okay. Now our last equation, we're going to sum moments, and we can sum moments about any point in the structure. What I'm going to do is sum moments about point A. We'll take these moments here to be positive. And I can pick any point, but typically what you want to do is write the equation that eliminates as many unknowns as possible. So by summing moments right here, two of the unknowns, AX and AY, pass directly through point A. So that means that by summing moments at A, I can solve for Bx. And so I just write out my equation of equilibrium, and so I take each force one at a time. So let's start off with the 9.81 kilonewtons. The first question is, does it cause a rotation at A? And the answer is yes. If I keep my finger fixed at A and I apply this 9.81 kilonewtons, it wants to rotate A. Now it's wanting to rotate A, in a clockwise fashion. So for example, if this is point A, this is the 9.81 kilonewtons, it's wanting to rotate it, like that. That is a negative rotation because I've assumed counterclockwise rotations are positive, and this is going to be clockwise. So we'll make that negative. And as for the distance, what we're going to do is use the moment arm. And remember, the moment arm is the shortest distance from the line of action of that force to point A. So it's that shortest distance right there. And that shortest distance for this is going to be 2 meters. So there's the moment there. And again, when it comes to signs, because we had a couple questions about this in class, the first thing that you should do is just make sure you've got the magnitude and the distance correct, the moment arm correct. The magnitude of the force, 9.81, the distance of 2 meters. As for the sign, you don't assign the positive and negative regarding whether or not the force is up or down, or whether or not the distance is to the left or to the right. It's whether or not the rotation is clockwise or counterclockwise. If it's clockwise, according to our sign convention, the sign will be negative. Okay, so the next thing we'll have is this 23.544 kilonewtons. It also causes a clockwise rotation, so it's going to be negative. Now its moment arm is going to be 6 meters. I think I can do better than that. 6 meters. Again, from point A, what is the distance from that line of action to point A? What's that shortest distance? And that shortest distance is 6 meters. Finally, Bx. So is what manner is Bx going to rotate point A? Well, if here's Bx, it's going to rotate it like that. So that's going to be counterclockwise rotation, so that's going to be a positive Bx. And the moment arm is, again, from the line of action to A, the shortest distance, that's going to be that 1.5 meters. And that equals 0. So now we just got to do a little bit of arithmetic. So 9.81 times 2, that's negative 19.62 kilonewton meters, minus, this is going to be this times 6, it's 141.264, plus Bx. And then we'll collect everything, all the numbers or the constant values over onto this side. So that plus that, if we chug that out, we're going to get 160.884. And then divide both sides by 1.5. We get a positive value, and we end up getting 107.26 kilonewtons. And that's positive because our math worked out that way. We'll call this equation 3. Now, really, any one of these lines could be considered equation 3, but really what I'm doing is just taking the simplest form. And as for the very last step, all we need to do is plug 3 into 1. So in other words, if you look at the 3 equations, I have a value for AY, I have a value for BX, but I don't have a value for AX, so I need to plug this BX term into that. So I get AX plus BX equals 0. I have AX plus 107.26. So therefore, now I've got my first negative term. So AX is negative. Okay. Now as for how do I express this? Because these were some questions that we had in class is how do we properly express the answer? Well, first off, so we have 3 reactions, BX, not BY. So the first thing that we need to do is recognize that these are vectors. So vectors have a magnitude and a direction. The magnitude is always a positive number. Think about when we had ij vectors. How did we calculate the magnitude? We would use the Pythagorean theorem. So we would never get a negative answer from that. So, sorry, I have my paper over that. So for resultant vectors, the magnitude's never negative because we would always use the Pythagorean theorem. So in terms of the magnitudes, we're going to use positive values. So this is, and then this is. So again, the positives or negatives that we have in these equations here, and for example in this box here, the reason that these values come out positive or negative is because they map to the sign convention that we've used up here. This sign convention is based off of assumptions. We assumed AY, we assumed AX, assumed BX, we assumed those directions. So the answers being positive or negative are just a function of those assumptions. Really, what is true for everybody when they do the problem correctly is the magnitudes and the actual direction. So for example, AY is actually acting upwards. We assumed a positive value, we assumed that AY was upward and we got a positive value. So it's actually acting upward. We assumed BX is acting to the right and we got a positive value. So it's actually acting to the right. AX, we assumed it was acting to the right and we got a negative value. So it's actually acting to the left. So this is our answer, or answers. And one of the things that we noted in class is that if you actually look at AX and BX, what do they form? They form a couple because we have 2 forces of equal magnitude and opposite direction. So it's actually really cool in that regard. That so if you follow the structure, what you see is that if you're looking, for example, at point A, the 9.81 kilonewtons and the 23.544 kilonewtons, those are both causing sort of a clockwise rotation at point A. So we need something to act against that. And so this AX and this BX, equal magnitude, opposite direction forces, are sort of causing a counterclockwise rotation to sort of bring the structure back into equilibrium. So that's why we have that going on here with this problem. Okay. All right. So like I said, so we had discussed this in class. I'm just taking what was on the board and sort of transposing it here onto the notebooks. That's why I'm going through the problems maybe a little bit faster. One of the things I want to do now is I want to focus on fixed supports. So I talked about this a little bit in class, but if you actually open up the textbook, there are oodles and oodles of different support conditions present in the book. And some of these, we'll use pretty regularly, such as the pin support, the roller support, what have you. The fixed support is what we're about to use now. But I should mention that some of these, like collars on frictionless rods and whatnot, we're not really going to use very much. Not to say that we couldn't come up with some interesting problems, but we're trying to cover the basics of statics in our course here. And so, you'll get experience with some of these more nuanced support conditions maybe in your specific fields. For example, kinematics of design of machines, maybe for you mechanicals, or structural analysis for you civils. But for the most part, we're just going to use the basics. And the one we haven't covered is a fixed support. So we're going to look at this problem here to assess a fixed support. And the thing about a fixed support is it's actually computationally easier to deal with than a pin support. With simple supports. With simple supports, we sort of had to be choosy about the order in which we solve the problem. So like, for example, if we go back to this, we did the problem in order. So for example, if you notice, we did the problem, we did the sum of the forces in the x direction, the sum of the forces in the y direction, and then the sum of moments. But we had to go back and back substitute, because if you remember equation 1, we didn't have an answer. We had just an equation that we knew we'd have to use again later. So we had to plug our value from equation 3 back into equation 1. That's not going to happen with fixed supports. With cantilever type systems like this you see right here, we're going to be able to solve for all three reactions directly because all of our unknowns are all going to be housed at point C. The only other thing I wanted to mention before I get into this is that this problem has three unknowns, and those are the three reactions at point C because point C is going to be considered our fixed support. We have a cable here, BD, and if you noticed I gave you the tension in cable BD. I said that the tension is this 1300 newtons. If I didn't give you the cable or the tension in that cable and you were required to determine that tension along with the other support reactions, then this would be an indeterminate analysis problem. And you can't actually solve indeterminate structural analysis problems with only equations of statics. You have to use some other facts like the relationship between applied loads and resulting displacements in order to be able to solve the problem. And so you'll learn how to do that in later courses in engineering. But for now, in rigid body mechanics, we have to limit ourselves to systems that are statically determinate. In other words, the number of unknowns match the number of equations of equilibrium that we have. So I'm going to go to our notebook here, and we're going to go through our example here. So one thing that I will mention is that this example is really mostly a bookkeeping example. It's not really difficult from a computational perspective. The math is going to be pretty easy, but the bookkeeping is really key here. Now, before we get to that bookkeeping, I do want to deal with this 1300 Newton force a bit. And so I want to deal with this cable. And the way that we're going to do that is we're going to look at the geometry of this wire a little bit and see if we can break down the tension in this cable into maybe an X and Y format that might make sense here. So let's look at this wire here. So what we're going to do, this is what we're going to do. So if I'm looking at my rigid body, let's say this frame ABC, this is my rigid body. So there's going to be reactions here at point C, but there's also going to be a tension force right there. So the cable is applying a tension to the frame. Okay, and this is, I'm going to call this tension force here, T. Okay, I know that the magnitude of T or T is 1300 newtons. But I'm going to see if I can break this down into X and Y components. Okay, so what I'm going to do here is I'm going to look at the wire. I'm going to say, all right, let's look at this. Okay, so we'll call this point B, call this point D. I have here on the schematic here, I have, this is 600 millimeters, not 600 meters, it'd be very long. Let's do that again. And this is 250 millimeters. I'm getting that from there and there. So in terms of this hypotenuse, the hypotenuse would just be, it would just be 600 millimeters squared plus 250 millimeters squared square root. And when you chug that out, this ends up being 650 millimeters. The reason why I'm doing this is because I want to get this tensile force in an X and Y component. And so the way that I'm going to do that is I'm going to take the magnitude times the unit vector. I'm basically going to use this format that we've seen in the past. So how am I going to do that? Well, I'm going to take vector BD, which from B to D, so let's think about this. If I'm going from B to D, I'm going to go a positive 250 units in the I direction, or in the X direction, so it's 250 times I, and then I'm going to go down 600 times J, okay? And let's make sure that we're documenting that with the units, okay? So that's my distance vector, and then remember we would take that and convert it to a unit vector. by saying that divided by the magnitude and then this is going to be unitless. And so if I have my lambda and I have my magnitude of 1300 newtons, I'm going to say that the tension vector is T times lambda and I'm going to get that. So that's going to be 500 I. So when you chug this out, so it's 1300 times 250 over 650, which is 500, minus 1300 times 600 over 650, which is 1200. And that is in newtons. Okay, the reason why that's valuable is because I'm going to replace this tensile force on point B. Instead of an angled force, I'm going to replace it with a force in the x direction and a force in the y direction. And so I'm going to have 500 in the x direction and 1200 in the y direction. So let's see what that looks like. Let's draw a free body diagram of the frame. So the free body diagram is going to be, so we're in rigid body equilibrium. So our rigid body is going to be the frame. So let's see what we can come up with here. So I'm actually going to redraw the frame here. That's probably good right there. Okay, so let's see. We've got a 750 Newton force here at A. At point B, we're going to have, okay, so this is going to be our 500 Newton force and our 1200 Newton force. And again, sorry, that's 1200, sorry. That's going to be our x and y components from the cable. So instead of applying a downward force of 1300, I'm instead applying a 500 and then a 1200. So that's what I'm doing there. Let's see. I also have this 450 Newton force right here. Okay. Now, in terms of my reactions, okay, this point C right here, this is a fixed support. So it's going to have 3 reactions. So what I'm going to do is I'm going to say it has a reaction in the x direction. It's going to have a reaction in the y direction. And it's going to have an unknown moment reaction. So if you're using just a pencil, sometimes the way that I will indicate unknowns is to draw a little tick through the arrow. So it's just sort of to say that that's an unknown. That's something I need to figure out for this problem. So if you want to do that for your calcs, that's fine. The only other thing I'm going to do is I'm going to apply some dimensions on this, just so I have everything all in one spot. So this dimension right here, this was 600. This dimension here is 400. And again, these dimensions. Oh, sorry. These dimensions. I'm just pulling this from up here so that they're all there. Speaking of, this is 500. This dimension is 150 millimeters, And I think that's, yeah, that's all of them. Okay. So like I said, so now we're going to apply our equations of equilibrium. I'll say a couple things. So it doesn't really matter what order we go in because all of our unknowns are located right here at point C. And then also we'll be able to get unknowns. We'll be able to get values from every equation of equilibrium. Let's see. I just want to make sure we're still recording. Yes, we are. Again, last time we had the recorder crashed out on us. I was just making sure that worked. Okay. Oh, one other thing I'll mention is that I also have a scenario here where at least one or more of the reactions are in the wrong direction. Again, if you assume a reaction direction and you get a negative answer, doesn't mean you need to panic or anything. Just means the reaction's going the other way. Okay. So let's start off by summing forces in the x direction. Just do it the same way we have been. My advice is to just treat this like a checklist. So one by one, check every single force off the free body. Do I need to consider this 750 right here? Well, no, it's a vertical force. Do I need to consider this 450? Well, yes, it's a horizontal force. And I'm going to write this as negative 450 because I'm assuming forces to the right are positive, and that's a force to the left. Here's that, plus 500. Do I need to consider that? Nope. And down here, I don't need to consider the MC. I don't need to consider the CY, but I do need to consider the CX. And there's my equation of equilibrium. So just solve it out. So I've got negative 450 and 500. So CX is negative 50. So if you want to describe that, what that would be is, at least in terms of an answer, is CX is a magnitude and a direction. And that's going to be one of our answers right there. So pretty simple. So hopefully that's sort of revealed here. If we sum forces in the y direction, let's move that over a little bit. So again, just a bookkeeping problem. Do I need to consider this? Yes, it's going down. Do I need to consider that? No. Do I need to consider that? No. Do I need to consider this? Yes. Do I need to consider that? No. No. Yes. Again, just treat it like a bookkeeping problem or like a checklist. Go through every one. I'm going to erase these circles though. Okay. So then it just becomes an algebra problem. Just solve. So minus 750. Or sorry, minus 750 minus 1200. So that's a negative 1950. And there we go. And since it's positive, how do we express that as an answer? We say a magnitude and a direction. And the direction is the direction that we assumed. All right. Okay. For the moments, this equation is going to get probably a little long, so I'm going to stick this down here. So sum of moments. And as for where we sum moments, I'm going to sum moments at C. Just because there is that moment reaction there at C. We'll see how we handle that. But it's the same idea. We'll just sum moments at C to sort of eliminate the CX and the CY from the expression. So sum moments at C. And then, let's see, we'll take that to be positive. Now, this equation is going to be a little longer because you're not asking about what forces are horizontal and what forces are vertical. You're asking which forces cause rotation. So, for example, does that cause rotation at C? Yes. Which direction does it rotate? Well, if you're this 750 Newton force, you're going to want to rotate point C like that. So is that a positive rotation? Yes, it's a positive rotation. As for what is the magnitude of that rotation, well, it's positive 750 newtons times a moment arm of, and it is the moment arm is defined as from the line of action. So there's the line of action of the 750 newtons to the shortest distance from that line of action to C, in which case this is 500 millimeters. So that's going to be our moment, and it's positive because it's generating counterclockwise rotation. So again, doesn't matter that the force is going up or down. Doesn't matter that the distance is left or right. That's not what's key. What's key is it causing clockwise rotation or counterclockwise rotation? And in this case, it's causing counterclockwise rotation, which we've said that's positive in our equation. Okay, so now what about that one? Does that generate rotation? Yes. Is it positive rotation? Yes. That's good enough. And as for the moment arm is going to be that line of action to the point that's going to be 400 millimeters. Okay. So next one, does that cause rotation? Yes, but it causes clockwise rotation. And the moment arm is from the line of action to C. So it's going to be that distance there, in which case that is 600 millimeters. Okay. What about the 1200? That also causes a clockwise rotation. And its moment arm is going to be 150. All right, let me scooch this equation over just a bit. Okay. Now, the only components that I haven't discussed are the reactions. Now, I don't need to consider Cx and Cy because they pass right through point C. But what about the moment? Does the moment cause a rotation at C? Well, of course it does. It's a moment. So I'm going to add MC. I don't multiply it by a distance because it's already a moment. So that's all I've got to do. And there's my equation. Now, at this point, same idea. Let's just start chugging this out. Now, I'll say at this point, I've got newtons and millimeters. So if you start multiplying this, the numbers are going to get pretty big. So if you want to, if in your calculations you want to go ahead and maybe convert the millimeters to meters, that might be fine. I'm going to leave it in millimeters, but the numbers will be pretty big. So chug this one out. This one's 375. So I'm 750 times 500, and the units are that. 450 times 400. Here, I don't think we need that plus anymore. So minus 500 times 600 is 300,000. Minus, and then 1200 times 150 is 180. So we start collecting like terms, start adding all this up. So the plus 180 and the minus 180, they're going to cancel. And so all we're going to be left with is 375 minus 300. So that's going to be 75,000. Plus MC is going to be 0, or and there we go. As for expressing this, again, it's a vector, right? So MC is going to be 75,000 Newton millimeters, or if you want to write it as 75 Newton meters, just, 1,000 millimeters in a meter, just, divide. You can do either one's fine. And as for the direction, this is a moment. So the direction is going to be a rotation. This was a negative moment, so this is going to be clockwise. Okay, hopefully you see that this is pretty straightforward and that this is a pretty simple calculation. If anybody has any questions, you know where to reach me, and you'll have a little bit of practice on this problem, on this topic, on a homework that's due Wednesday. And that's all we have. We'll see you.